Okay, so this is my first experience of talking about probabilistic programming and machine learning to an audience which is not focused on probabilistic programming and machine learning. So I'm going to share my excitement when I first learned this field. And sorry. So first, what probabilistic programming is. Probabilistic programming is an idea of expressing statistical models as general programs. And statistical models are when you have some variables which are connected but not deterministically connected, and you know probabilities about some of the variables, and you know about some of connections but not all of them, and you have some observations, that is what you can measure, and you want to know something about you cannot measure. And because you cannot know that deterministically, that's called statistical model. And here is a probabilistic program which connects between positive mammogram and breast cancer. So the program basically says that breast cancer happens with probability of 1%. A benign cyst, it happens with probability of 20%. And positive mammogram may follow from breast cancer with probability of 80%, and from the benign symptom from probability of 50%. And then what happens is that if we observe a positive mammogram, what would be the probability of breast cancer? That's what this program says. So that looks like a random run, but that's actually not a random run, because we don't want to know what happens if we have breast cancer with positive mammogram. We want, in a way, to run this program backwards. So probabilistic programs are actually programs which compute posterior distributions, what we know about variables given observations. And our program was a very simple program, but the programs can have conditions, loops, unknown number of variables, recursions, and so on. And what's important about programs is that despite the flip-like random sampling in the programs are mostly deterministic. So what they say is they say something about probabilities, and rather than about sampling. We can think about a probabilistic program which samples something like random stochastic probabilistic program, but most probabilistic programs are just models which connect probabilities. And once we wrote a probabilistic program, we need to run it to compute certain probabilities. But what we know is at the end of the program, like that we observed a positive mammogram. And what we don't know is the beginning of the program. So we somehow need to run the program backwards. And since we do not know how to run programs backwards in general, we use all kinds of approximate algorithms to infer approximately probabilities about unknown variables in the program. And this area has become recently, in last probably 10 years, but the explosion is last 5 years or so, very popular and fashionable, because instead of using limited statistical models, like graphical models, like linear models, you can write any program, include any distributions, and reason about unknown variables, and describe very complicated simulations. And what do people do when they want to write programs according to new paradigm? They invent a new programming language. And so there are 45, 50, that's an old slide, 50 probabilistic programming languages in Wikipedia. There were about 20 probabilistic programming languages presented at the first conference of probabilistic programming. And not all of the language intersect, so this is exploding. Every single person who comes to the field of probabilistic programming, where the promise is that we give you the programming language and you write all of your models in the same probabilistic language and solve your problem, and the person actually invents a new probabilistic programming language. And there is something wrong about that. If the promise of probabilistic programming is that you don't have to reinvent the tools, then why every single one invents the tools, new language, new paradigms, new semantics of language, and so on? There must be a reason behind being able to publish a conference like Popple. And there must be a solution that actually allows people to reuse approaches and use probabilistic programming languages in practical settings. There are two views on what probabilistic programming is. One view is that it's a framework for statistical computing. You get some data, you have a data scientist, or you are the data scientist. You, as the data scientist, write your statistical model as probabilistic program, and you do some analysis, and you have some insights, and you share those insights. And then your program may exist in an isolated environment on your computer, and you do not connect your program automatically, programmatically to anything else. Another view of probabilistic programming, and that's the dream actually, and the reason why probabilistic programming came into existence, is that it's an inferential program. It's an algorithm which actually makes a decision. It's a part of a bigger system. And as a part of the bigger system, it has some parameters, many parameters probably, which can be learned, inferred at the time when the program runs. So that as the program runs, it adapts to changing conditions. But that part of the program which runs is a part of a bigger system which does not include a man in the middle to make the decision, but connected automatically. So when you want to implement a probabilistic program as a part of a larger system and make it a functional module, functional unit in the system, then there are certain challenges in making it interoperate with the systems. And those challenges is the paradigms of simulation versus inference. I will be talking about it in detail in moments. Handed data coming from different sources in actual deployment of probabilistic models. So what simulation versus different is? Versus inference is. A probabilistic program is in a sense a simulator, and it can contain, or it contains its simulator as the right part. You have some process which reproduces activity you want to perform, and you have some unknown parameters of the process. And then your probabilistic program using inference algorithm, based on inference algorithm, run that program, including that simulation process multiple times to infer the right parameters, hundreds of thousands of times. And then you found those parameters. And then you want to use those parameters to actually predict something, to actually control the robotic arm, to actually make the diagnosis. So the model as it is here, this is just linear regression here. And the simulator share the same source. In this simple example, this is a single line which computes linear regression, a plus bx. But in a bigger system, you want the same code to be shared by probabilistic program and by actual simulation. And that's hard to do if all you have is a special language probabilistic programming. You would have to rewrite that part in a different language or find an awkward word to reuse it. And another problem comes from data structure bias present in machine learning. For machine learning, for modern machine learning, the tensor, which allows efficient computations on certain architectures, is the basic data structure. And someone who invents a machine learning library or probabilistic programming system uses what is efficient for machine learning. And what is efficient for machine learning is not necessarily efficient for writing advanced, like forward propagation of deep learning networks, not necessarily efficient for writing rich algorithms, rich simulators, explaining complicated, involved graphic, probabilistic statistical models, which probabilistic programming is about. So this simple piece of code is what I want to write. I want to update a single element of the of an array. First initialize it to once and then update it. But I cannot do it in tensors. And what I write in practice in probabilistic programming languages, because they are not created for my actual algorithms, I write quite a lot of code which looks like machine learning assembly. This is just multiplying a single element by a certain number, and this is what I need to write because I use a wrong language. And the last point is deployment. If I want to deploy a probabilistic programming module in a larger system, and I work in a startup which does a lot of machine learning and probabilistic programming computation in production, I need to bring along all the support libraries, very nice, which support a statistical probabilistic programming environment. And that may range from 100 megabytes to 1 gigabyte for different, those are different probabilistic programming languages. All of those are good. But you want to bring a lot of dependencies. Most of those are not needed for my small programs, but for everything in the world which can be expressed by probabilistic programming in this particular probabilistic programming language. And these are not just 1 gigabyte of dependencies. This is 1 gigabyte of possible bugs. And in a production environment, 1 gigabyte of possible bugs is quite a lot. No DevOps engineer, no integration engineer would look at it with a good eye and say to me, okay, you want to tune 2 parameters in your program, just bring me 1 megabyte of bugs which I never tested and never checked. So combining my experience as an academic researcher and as a scientist in a startup, I came up with guidelines for designing a probabilistic programming system which can be deployable, which can be deployed as a part of a system. And these guidelines is the same language must be used for the host system and for the probabilistic programming modules, and that's possible. The probabilistic program, a probabilistic program should share the same data structures as the host system. If you have arrays, hash tables, pointers, and lists, streams, and whatever in your host system, you should be able to program in the same nature way in a probabilistic program. And that should lead to the fact that code used for simulation, for prediction, for forecasting, for guiding robotic arm, for making medical diagnosis should be the same, should be written once for the host system and for the probabilistic program, for practical module. And the idea is to implement this as a reference implementation in the Go programming language. And this is a very non-conventional choice for machine learning, but turns out it's a good choice because Go is small, expressive, efficient, and popular for server-side programming. It's a very nice language to program in. It doesn't support vector operations on just like Python and NumPy support, but it's fast without vectorizing. And it uses very nice tools to allow you to express your models. So when you talk about probabilistic programs, the thing which you write is called a model. And a model is a program. And since any probabilistic program, in fact computes a probability of something, and in general, machine learning is about computing probabilities, so probability densities. So the model is just a data structure which has a type, which has a single method, observe, which gets the parameters which you want to tune, and computes the log probability of your observation in one way or another. In this simple example, we estimate parameters of normal distribution and so on. So this looks like a probabilistic model written in other probabilistic programming language. In Stan, I will show examples later. In Turing, I will show examples later. But in fact, it's pure Go code because it leverages only language, basic language constructs. And the model must obtain data. And the simplest way is to pass the data array in the data structure. And that's what we can do in any probabilistic programming language and in Go too. And Then when we have the model and the data, we can just run some form of optimization. This is stochastic gradient descent, which obtains the model as a parameter and runs the optimization on the model, M as the model, is X as the parameter. So that's what you basically do with the model, optimize the arguments. Or you can use a more advanced algorithm to recover the full distribution. But what makes this approach of simulating, expressing probabilistic programming in a host language rather than in a different language is that if you, instead of using something hard-coded in the language, like data source, like a representation of data, replace with a different structure, you can just use it, do it using the language means of the language. Go has streams. It's like channels of data, pipes, which you write on one end and read from the other end. And if instead of passing an array, I want to stream data continuously, all I need to do is to modify the definition of my data structure and include the stream field and to read the observations from the stream here instead of taking them from the data array. That's because I implemented my probabilistic programming system in a general purpose language without going into re-implementing and reinventing a new language. So there were different experiments in implementing probabilistic programs on what looks like a general purpose language. There was a probabilistic programming system in Clojure, Anglican, and there are a few probabilistic programming systems in Julia, and Julia is a language for statistical computing. But you do not write systems in Julia, and it's hard to integrate Julia and statistical and systems. But Go is simple and elegant language, which comes with the parser and type checker. You do not parse Go code on your own. You use a library, you get the abstract syntax tree with type information attached. That allows you to use just generic Go code and manipulate it as you need to achieve a probabilistic programming inference. Go compiles and runs very fast. This is probably not the first thing to talk about server-side programming, but if you think about probabilistic programming in statistical model in general, this is trial and error. You run and modify your program again and again. In many, even compared to interpreted probabilistic programming systems, you get in under a second a new version of the model. You can experiment with the data and so on. And another thing which is very useful for statistical inference in Go is how it was created for entirely different purposes is Go routines. A way to spawn 100,000 parallel threads and use it for parallel computation. That's very good for sampling. That's very good for inference. So the system I wrote is called InferGo, and models are written in pure Go, and the system relies on automatic differentiation for inference, and a few words about it in a moment. And it works in a way where Go does. It has no internal dependencies, and it's free to use, and we use it, and we see others using it, and it works. So another thing which is, before the next slide, is automatic differentiation. Efficient statistical inference is based on automatic differentiation. There are three ways to differentiate a function. There is a symbolic differentiation when you use analysis differentiation rule, the chain rule. This is numerical differentiation when you have a small difference in the argument. You compute fraction values at those two values, and you compute the ratio. And there is a third way, which is called algorithmic differentiation. That's when you take a program and you differentiate it into another program which when run computes the numerical value of the derivative exactly. This is the third way. And modern probabilistic programming system, modern machine learning systems use differential programming automatic differentiation to compute the gradients. when deep learning does backpropagation, it's a reduced case of the automatic differentiation. You can differentiate any program. And I want to get, yes. Sorry. To automatic differentiation here. Okay. So when you have the code of a program, you want to run it in such a way that you record information necessary to compute the gradient afterwards. That's called reverse mode automatic differentiation. It works like that. You run the program forward, and you write down on a special structure, which is called the tape, the operations on your numerical floating point data types which you perform. Then you run the program, run the tape backward in a certain sequence in such a way, according to the differential rules, that at the very end, the gradient, the derivative is computed. There are several ways to implement automatic differentiation. And a normal way to implement automatic differentiation is to use a type overloading. Create a special type when you do every construct, every floating point operation on the type, you end up with a small record, small note of what you did on your tape, and then you can run the tape forward. An advantage of that is that it's very easy to implement. A drawback of that is that you cannot use any other library with your probabilistic programming library, because your floating point type is not your built-in floating point type anymore, and you lose connectivity. Instead, InfraGo implements automatic differentiation on a native type and rewrites the model by these system calls, so that this is the recompilation, rewriting of the model code, where assignment is replaced with assignment call, function call, function call to the function call, and so on. And those functions write information to the tape, but operate on the built-in point, floating point type. And this approach is possible because Go gives you parser and abstract syntax tree and type checker for free. And this approach lets you use built-in floating point type for all your statistical computations. And because that happens, you can use third-party libraries for inference as well as your own. So a few simple examples to show how much of a cost you pay for using a standard probabilistic programming language instead of custom probabilistic programming language just for domain-specific language, just a person. On the left is a program for a well-known benchmark written in Stan. Stan is a well-established probabilistic programming system. On the right is the same model in Go. It has roughly the same structure. I didn't make any special effort to do that. Data definition, parameters, and inference, and model dependencies on the parameters, except for the loop in the InfraGo model. But Stan loops are very slow because there are 5 layers of APIs to pass to the data, and Go loops are fast. So you actually can write models in the same structure using a general purpose programming language as a special purpose DSL. And DSL is not always the solution for these cases. And in other examples, linear regression. And an example of linear regression is that I do something I can hardly do in many other probabilistic programming languages, because this is my model, and my model has a call to simulate. And simulate is just computation of this linear function, but it can be very complicated. And because it's InfraGo, I can just define a method and use that method once, automatically differentiate it in the model, and the other type in the simulation when I don't need the inference, and I reuse the code, and I make and fix my bugs only once, and I can use it efficiently in deployment. A few words about applications. I didn't put it on the slide because it's a long story, but the startup I work for part-time makes money by monetizing advertisements, helping people make money from ads in the content. That's like not very sexy business, but it's actually a source of many problems suitable for probabilistic programming. It's time series forecasting, structured models for predicting which of campaigns or advertisements will be fine, which will be not, and so on. And because we did deploy the whole system in Go and could implement our probabilistic part as small modules, which are very cheap to deploy, we actually went from rule-based algorithmic solutions to deploy probabilistic programming, advanced machine learning algorithms, the state-of-the-art of machine learning in production systems with the target function of loss and reward. Very simple. The number of dollars or thousands of dollars you earn or lose every day, and we actually earn more by using deployed probabilistic programming in the system. I'd like to thank the people who introduced me, and the final thing is Infergo has a mascot, and this mascot is the gopher of Go with like this trident of Inferno, because Infergo is like Inferno. Thank you. Questions?
We have time for one or two questions.
Sure. So it's not immediately obvious to me how you use automatic differentiation to do inference over a program that generates recursive data structures probabilistically.
Automatic differentiation. So the question is where you can be sound in computing probabilities on recursive algorithm data structures. But like statistically, whether if you have a recursion or variable number of variables, you are statistically sound. But that question aside, there are many models which actually do that, model that, and provided you have such model, you can use automatic differentiation. Automatic differentiation doesn't look at the structure of the code in general, but only on the sequence of operations which were performed in the particular trace of executing the program. And on each execution, the program has one particular trace.
Sure, but when you do inference, you may change the number of stochastic choices you make and change the structure of the trace that way.
Right. Traces change from execution to execution, and there are problems of discontinuity of gradients and scientific research on that. And this work, there is large body on research on that, and there are many systems and theoretical work on that. And this is indeed a problem. And there are algorithms which identify discontinuities and know how to deal with that. But from the point of view of basic implementation of differentiable programming, you just don't look at that. You assume that your program is sound, and what you do, you just compute the gradient at the point where the trace was computed.
So you don't change the number of stochastic choices in a trace. You don't change the structure of the trace and the structure of the data structures that are built as part of your inference algorithm.
Automatic differentiation is dynamic. You don't differentiate once and for all. You record dynamically what happened in that particular trace and compute your derivative relative to that particular trace. And when you have a different trace, you will get a different derivative and a different computation of the derivative. It's not like getting a new hard-coded formula.
Okay.
We can take it offline, no problem. Yeah.